In this lesson, we're going to talk about matched or paired samples. Now, in many statistical applications, we use paired samples to draw conclusions about the difference between two population means. And these are going to be dependent samples. And the data pairs are going to occur very naturally between before and after situations. The same object is going to be measured before and after some kind of treatment. And there's a lot of applications to this in social sciences and natural sciences and in business administration. And they usually involve a study of matching these pairs up. When we're working with paired data, it's really important that we define a uniform method of creating the data pairs that clearly uses matching of the characteristics. So let's walk through the couple examples so that you can see what we're talking about. So in the first example, it says, a shoe manufacturer claims that among the general population of adults in the United States, the average length of the left foot is longer than that of the right. To compare the average length of the foot with that of the right, we take a random sample of 15 U.S. adults and measure the length of the left foot and then the length of the right foot for each person in the sample. Is there a natural way of pairing these measurements? And how many pairs will we have? So in this case, we're going to pair each left foot measurement with each right foot measurement. So we want to make sure that the left foot and the right foot that are being paired up are coming from the same person. So that person is serving as that matching link between the two distributions of the left foot and the right foot measurements. Now, because we're measuring 15 people, there's going to be 15 pairs. So there's going to be 15 left foot measurements and 15 right foot measurements, and then when we pair them up, it's going to be 15 pairs. So these are dependent samples. Let's look at the next example. A psychologist has developed a series of exercise called Instrumental Enrichment Program, which he claims is useful in overcoming cognitive deficiencies in children. To test the program, extensive statistical tests are being conducted. In one experiment, a random sample of 10-year-old students with IQ scores below 80 was selected. An IQ test was given to these students before they spent 2 years in the IE program, and an IQ test was given to the same students after the program. Now the question says, on what basis can you pair the IQ scores? If there were 20 students in the sample, how many data pairs would you have? So if we take the before IQ scores and the after IQ scores, and we're talking about before and after being in this program, the IE program, that would create the pairs. So for each student, you would take their before score and their after score, and that would be a matched pair. Now, if there were 20 students in the sample, how many data pairs would you have? We would have 20 pairs because we have 20 students and they each have 2 values that are paired up, and there would be 40 IQ scores in total. So let's walk through the first example. This example talks about a heart surgeon that is concerned about his patients because when they go through heart surgery, they have a lot of anxiety about the surgery. So he gets together with the hospital psychiatrist and they go do some tests to see if counseling will help them with the anxiety dealing with this heart surgery. So what they do is they get the patient and they test them for their level of anxiety. That's before the counseling sessions, and they put them through some counseling sessions to help them cope with the anxiety of the surgery. And then after the counseling sessions, then they give them another test to see where their anxiety level is at. So here's our matched pairs. They're dependent samples because they're matched up, where they're taken from the same patient, the same measurements to see a before and after situation. So this column B represents the anxiety scores before counseling. Then column A represents after counseling. And the question is asking, from the given data, can we conclude that the counseling sessions reduce anxiety? And we're going to use a 0.01 level of significance. Now, when we do hypothesis testing with matched pairs, the whole procedure, the 5 steps, are virtually the same. We switch the symbols that we use for a hypothesis, and we use a different test statistic formula. But other than that, the idea, the concept for each step is going to remain the same. Now, when we find the test statistic by hand, for those of you who like to use the formulas, the formula for the test statistic is going to be D bar times the square root of n, which is your sample size, over the sample standard deviation. Now that D bar is going to come from the differences between the matched pairs. What we're going to do is we're going to find the difference. I'm going to extend over here and create a third column. And this third column is going to give us the differences between these matched pairs. And then when I average all those values, that's my D bar. So I'm going to take the difference between 121 and 76. That gives me 45. I'm going to take 93 minus 93. That gives me 0. 105 minus 64. That gives me 41. And I'm going to go down and I'm going to find all of those differences. Okay, this is, I'll call this our D's. That's our D column. It's the differences between our matched pairs. Now, if I average all these values, that's your D bar. Okay, so when we do a hypothesis test on matched pairs, we're always going to set up our null hypothesis as mu sub D, and that little d reminds us that we're doing matched pairs. We're going to use the notation mu sub D, and that little d represents the differences between the matched pairs. So that reminds us we're not just doing this on the difference between means, but this is specifically for matched pairs. We're always going to set it up where I have mu d is equal to 0. Now, for the alternative hypothesis, we're going to have either mu sub d is not equal to 0, less than 0, or greater than 0. Those are our 3 choices. Now, for us, in this specific example, we want to see if the counseling sessions help reduce anxiety. So we're looking to see if these scores here in the first column before counseling, and then we look at the second column, which is the after counseling, we want to see if that second column is going to be consistently lower. So if that second column is lower, and we're calling this mu1 and this mu2, when I subtract them, if mu2 is smaller, and I take mu1 minus mu2, then mu sub d, the difference between the two, has got to be greater than 0. And then, of course, we're using, based on the question, it asks us to use a 0.01 level of significance. Now, in step 2, just as normal, we want to find our test statistic and our p-value. When we're doing matched pairs, we always want to use the student's t-distribution. And on the calculator, we would use t-test. If you're doing it by hand, here's your formula for your test statistic. So let me hop over to my calculator and I'll show you how you can enter in all this information. Okay, so to put this in on the calculator, you want to go to Stat and you want to go to Edit. And I already have my values in there preloaded, but go ahead and take a minute and you're going to put the first column of values in your L1. That's your B value, the scores before counseling. And then in your L2, you're going to put your A column, which is the anxiety scores after counseling. So go ahead and pause the video and enter those values. Once you enter those values, instead of calculating all those differences by hand, what you can do is you can highlight your L3 column, and then in the name where it says L3 and it's highlighted, you can actually put L1 by choosing second one and accessing the L1, and then I'm going to put in minus L2. And it's going to take all these matched pairs and take the corresponding values and subtract them and then line them up in the third column. So then I'm going to hit enter and it calculates all of those differences for me very quickly. So you can see if I take 121 minus 76, that gives me 45. If I take 93 minus 93, that gives me 0. So that saves us the trouble of doing all that arithmetic by hand. Now, once we have our differences, we are going to run our test using the column that has all of our differences in it. So make sure you pay attention to which list you have those values in. So then once we're ready to run our statistics test to get our t-test value and our p-value, we're going to hit the stat button. We're going to go over to test, and I'm going to do a t-test, and then I'm going to hit enter. This time, I'm going to use data because I have all my information in that list 3. So now I want the calculator uses the notation mu sub 0. We use mu sub d, but it's the same thing. You want this to be 0. And I'm going to go down and tell it which column I have my differences in. And I put mine in list 3. So I'm going to make sure that that says list 3. Leave the frequency alone, and then you choose the type of test you're going to use. Since we were testing if the differences in the means are greater than 0, I'm going to use the right-tailed test. And then I'm going to go down and I'm going to hit calculate. And it's going to give me my test statistic. If we round it to 2 places, we get 4.36, and it gives me my p-value of 0.0012. So we did a right-tailed test. I forgot to write that down previously. And then when we did this on the calculator, we got that our test statistic is 4.36 and our p-value is 0.0012. Okay, now let's go on to step 3 where we do the rejection region. Since this is a right-tailed test, I'm going to be looking at the right tail to set up my rejection region. 0, of course, is in the center. Now, because we're using a student t-distribution, when I find my critical value, I want to use inverse t, and I put in my percentile and my degrees of freedom, and you should get that your critical value is 2.896. And don't forget where that red shaded area comes from. It's because we're doing a 1% level of significance. So we're looking for that shaded area that gives me 1% or 0.01. Now, when I look at my test statistic is 4.36. So that is to the right of 2.896. That's going to be on this side of 2.86. So that tells me since it's in the rejection region, we're going to say for step 3, reject the null hypothesis. Okay, step 4 is using the p-value. So we got for our p-value, we got was 0.0012, and that's definitely less than 0.01. And whenever the p-value is less than your alpha level, we say reject the null hypothesis. So we got reject for both steps. That tells us we're on the right track. So now I have to write out my conclusion. So we're going to say at the 0.01 level of significance, there is enough evidence to suggest that the counseling sessions reduce anxiety. If you recall, when we set this up at the beginning, the null hypothesis is that there was no difference in the muse. This alternative hypothesis is telling us that the second mean, which is the counseling after, which is the scores after counseling, is smaller, which is why we have a mean difference that's greater than 0. So since we're rejecting the null hypothesis, there is enough evidence to suggest that the counseling sessions would help. At our second example, do educational toys make a difference in the age at which a child learns to read? To study this question, researchers designed an experiment in which one group of preschool children spent 2 hours a day for 6 months in a room well supplied with educational toys, such as alphabet blocks, puzzles, ABC readers, coloring books featuring letters, and so forth. A control group of children spent 2 hours a day for 6 months in a non-educational toy room. It was anticipated that the IQ difference in home environment might be uncontrolled factors unless identical twins could be used. Therefore, there's 6 pairs of identical twins preschool age were randomly selected. From each pair, one member was put in the room with the educational toys and one twin was not. We're going to use a level of significance in 5% and test the claim that the experimental group learned to read at a different age, either younger or older. So these are definitely our pair differences or our matched pairs. So each set of twins represents a pair, and then they take one twin and the other twin and they put them in the 2 different rooms, which creates that matched pair. I'm going to skip this column here of putting in the pair differences unless you actually want to find those subtraction values yourself by hand. I'm going to use the calculator in step 2 like I just showed you. So in step 1, we're going to set up our null hypothesis to be the mean differences is equal to 0, and then the alternative that the mean differences is not equal to 0, because the question specifically says we're looking to see if it's different, not if it's younger or older specifically, just if it's different. Now, if the means were the same, when I subtract them, I get 0. So the null hypothesis is suggesting that the means are the same. If I suggest that the means are different, when I subtract them, then the subtraction is not going to be 0. So the means are the same. And then this one, the alternative hypothesis, this notation is telling me that the means are different. Okay, and we're doing this at the 0.05 level of significance. Because this is matched pairs, we're going to use a t-test. And then this is going to be two-tailed test. So let's switch over to the calculator and see what we get for our test statistic and our p-value. Okay, so I'm going to go to the stat button and into the edit option, and I'm going to make sure that I have my matched pairs in L1 and L2. So I put the experimental group in L1 and the control group in L2. Then once you put your data in there, what you want to do to make sure that you get your differences in the last column, you are going to make sure you're highlighted on the actual name of the list, L3. And then you're going to tell it to do L1 minus L2. And then when I hit enter, it will automatically find all those differences for us to save us the work of all that arithmetic. Once I have the differences, then I can do my t-test, and I just make sure I do my t-test on that list of my differences. So I want to make sure when I go to t-test that I'm on the data option. My mu is 0 because we're doing paired differences. You tell you tell the calculator which list you're using for your paired differences. Leave frequency alone at 1, and then you choose the correct option for our test. We're doing our test as a two-tailed test. So I'm going to pick the does not equal option. Then I'm going to hit the calculate option. And we're going to get that our test statistic is negative 2.64575, and our p-value is 0.045659. So let's go ahead and finish our hypothesis test now that we have that information. Okay, for our test statistic, we get negative 2.646, and for our p-value, we get 0.045659. So for step 3, for our rejection region, we're going to have that this is two-tailed. So we're going to look at both ends of the graph. Now, for our critical value, because we're splitting this into two tails, my alpha level is 0.05. So when I look for the area under the curve, that's going to be 0.025 because I'm splitting it in half. So I'm looking for the test statistic that gives me these cutoffs, not 0.05, 0.025. When you use inverse t to find that, you're going to find that it's 2.57 and negative 2.57 for those cutoffs. Now, when I check my test statistic, we got a test statistic of negative 2.646. That's passed to the left of negative 2.57 right in here, which means it falls in the rejection region. So we're going to say reject the null hypothesis. Now for step 4, we're going to use the p-value. We got our p-value to be 0.04659, and that is less than 0.05, which is our alpha. So again, because the p-value is less than alpha, we're going to say reject the null hypothesis. So for the conclusion, I'm going to write at the 0.05 level of significance, there is enough evidence to suggest that the experimental group learned to read at a different age.